Let us look at concavity, convexity, and point of inflection. Let's look at it with an example. Let's say we have this graph. This graph is f of x equal to natural log of x. Now here if you notice that it is concave downwards and it is convex upwards. So instead of every time talking about concavity and convexity, we restrict ourselves to only concavity because convexity would be the other side. Okay, so here let's take a point A and let's draw a tangent at A. Now if I go along the x-axis, do you notice that the tangent's slope is decreasing? So here, how do I figure out the slope of the tangent? I differentiate it. Dy by dx equal to 1 by x. And here, as x goes to infinity, 1 by x goes to 0. So it is decreasing. Now when I take the second derivative, that is the rate of change of the slope of the tangent, I get minus 1 by x squared. And this is always less than 0. Because even if I take a negative x, which in this case we can't because natural log x, the domain is greater than 0. X square will make it positive. It means it is throughout less than 0. So if the second derivative of a function is less than 0, then we say it is concave downwards. Now let's look at the second example. This graph is for what? This is for e to the power of x. Again, we take a point on that and we take the tangent at that. So again, if I go along the x-axis, you will notice that the slope of the tangent keeps increasing throughout. And we know that the slope of the tangent is the same as the function itself. So here, as x goes to infinity, e to the power of x also goes to infinity. And if I take the second derivative, that is also e to the power of x. And in this case, it is always greater than 0. That means it is concave upwards. Now let's look at a function like this. Now this is somewhere above, looks like a parabola. But is it a proper parabola? Let's explore. Let's take the first derivative. We get this. Again, if we want, we can take a point on that and take that tangent. And as we move, the tangent keeps changing, or the slope of the tangent keeps changing. But it's difficult to make out how exactly it is changing. So let's take the second derivative. We get 12x square minus 36x plus 24. Now we have to see whether the second derivative is greater than 0, less than 0, or equal to 0. So before we actually look at that, let's factorize it. We get this 12 times x minus 2 times x minus 1. When will it be greater than 0? So this will be positive when x minus 2 is positive and x minus 1 is also positive, or when both of them are negative, which is what is mentioned here. So d2y by dx square is greater than 0 when x minus 2 is greater than 0 and x minus 1 is greater than 0. Or x minus 2 is less than 0 and x minus 1 is less than 0. So which means d2y by dx square is greater than 0 when x is greater than 2 and x is greater than 1, or x is less than 2 and x is less than 1. X is greater than 2 and x is greater than 1. So we just have to stick to x is greater than 2, because when it is greater than 2, it is automatically greater than 1. So these we can combine into x is greater than 2. Now here x is less than 2 and x is less than 1. We can combine them into x is less than 1. So which means it is concave upwards when x is in the interval minus infinity to 1 or in the interval 2 to infinity. Okay, that was when the second derivative is greater than 0. Now what about when it is less than 0? So d2y by dx square is less than 0 when, now think about it, when will this be negative? When either this or this is negative. They both can't be negative. So when x minus 2 is greater than 0 and x minus 1 is less than 0, or x minus 2 is less than 0 and x minus 1 is greater than 0. So let's simplify that. So d2y by dx square is less than 0 when x is greater than 2 and x is less than 1, or x is less than 2 and x is greater than 1. Now here if you notice, x is greater than 2 and x is less than 1 is not possible. At the same time, it can't be greater than 2 and less than 1. So we ignore this case. So we are left with this case. So what this means is that the graph is concave downwards when x is in the interval 1, 2. What happens when it is 0? So let's take that case now. So d2y by dx square is equal to 0 when any one of them is 0. So either x minus 2 is 0 or x minus 1 is 0, which means x equal to 1 or x equal to 2. Now, when x is equal to 1, if we substitute it here, we get y is equal to 19. And when x equal to 2, we get y is equal to 33. So these are the 2 points where the curvature flips. So these 2 points are called the points of inflection. Now remember, in case of natural log of x and in case of e to the power of x, there were no points of inflection because they were concave downwards throughout or concave upwards throughout. But here it is changing. Now let's look at another example. Y is equal to sine x. Let's take a point on that. Let's bring it here and let's draw a tangent. Now, as I move along the x-axis, you will notice that the slope of the tangent increases and decreases periodically. So let's understand this behavior. So first is to figure out the derivative. So dy by dx equal to cos x. And now we take the second derivative, d2y by dx square equal to minus sin x. Now we have to figure out when is it greater than 0, because in that case it will be concave upwards. d2y by dx square is greater than 0, which means minus sin x is greater than 0. To get rid of this minus sign, we multiply both sides by minus 1. So we get sin x is less than 0. So when is sin x less than 0? When x is in the interval 2n plus 1 pi, comma 2n plus 2 pi. So here, let's take one particular case. Say n equal to 0. That means we have pi. Here if we say n equal to 0, 2 pi. So pi to 2 pi. Pi to 2 pi. It is concave upwards because that is where d2y by dx square is greater than 0. d2y by dx square is less than 0, implies sine x is greater than 0. And when is sine x greater than 0? When x is in the interval 2n pi comma 2n plus 1 pi. Again, let's take one example. Let's say 0, n equal to 0. We get 0 comma pi. So 0 to pi. Sin x is positive. And here, that means that it is concave downwards when x is in this interval. d2y by dx square equal to 0. Figure out the points of inflection, which means sin x is equal to 0. And when is sin x equal to 0? When x is in n pi, multiples of pi. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, minus 1 pi. So points of inflection are n pi comma 0. So these are the points at which the tangent changes its direction of movement. Here it is reducing, 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 reducing. And now again it is increasing now. So that is concavity, convexity, and points of inflection. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it. And if you think somebody else can also benefit from it, please do share. That's it for now.